and introduced the basic stuff more or less slowly, and I hope you could follow me. Then please, now we can accelerate to discuss 45 slides within 40 minutes. Yeah, maybe it will work. Yeah, I hope. Well, regarding the initial conditions, as we already said, the form of the initial conditions is determined by this projector operator, by the second fundamental theorem. So you see here the form of the initial condition. You see here this basis function kappa that of course belongs to the series, and therefore, if we consider initial value problem for this operator, then the natural form of the initial condition is this one. And if we fix this initial condition, then we get this form of the solution. Of course, the same method can be, or its particular case of the Riemann-Liouville fractional derivative, the kernel is the power law kernel, and then if we write down the solution, then of course it's a known solution, yeah, in terms of the Mittag-Leffler function. The same method can be applied to the inhomogeneous relaxation equation under the condition that the source function can be represented also as a convolution series, and the unique solution of the corresponding initial value problem with this initial condition is like this one. So it's the term that corresponds to the homogeneous problem, and this is convolution of the function f, the source function with the same kernel L kappa lambda. Well, in the case of the Riemann-Liouville fractional derivative, the form of this of the solution is also well known, same form with the Mittag-Leffler function of two arguments. Then, of course, we can consider the multi-order equations with the sequential derivatives, also with the source function, in form of convolution series. And if we substitute convolution series with unknown coefficients for the function y, then of course we get some equations for the coefficients, and in this case the first n coefficients are arbitrary constants, and then if we took them as arbitrary constants, we can calculate other coefficients step by step from this equation and get the explicit form of the solution of this equation. These constants, arbitrary constants, can be uniquely defined from the corresponding initial conditions. And as you remember, the projector operator for this sequential derivative in the Caputo sense and full derivative looks like this, and this means that the basis functions are n-fold convolutions of kappa. So you see that the natural form of the initial conditions is this one. And if we fix this initial conditions, then we fix this constants and we get a unique solution. Well, of course, this method can be used for equations with non-constant coefficients, for equations with polynomial coefficients, and so on. Of course, it's pure theory, and the question was if these equations could be potentially useful for applications. Of course, very interesting, more or less open until now, and still mathematics mathematics deals not just with applications. Of course, applied mathematics deals with applications, but in general, one develops some theories and then one hopes one day they could be useful. But in this case, there was already a series of papers devoted to applications. I will refer to these papers. of applications with of differential operators of exactly this type. So Vasily Tarasov from the Moscow State University published recently a series of papers where he tried to generalize several physical theories of electromagnetism and theory of other processes to the non-local case. And he developed also vector calculus, I mean a space version of this differential operators based on these operators, and using the vector calculus for these operators he tried to formulate in fact new more general physical theory for several things. I will refer to his papers later on. You can look at them. Well, now I would like to show you another story. That is it means another method for solving, in particular, fractional differential equations, so-called operational calculus. The history of operational calculus is a long one, started from works of Leibniz, and the idea is to interpret differential integral operators as some algebraic operators. So Leibniz introduced them as algebraic operators. Then Heaviside used algebraic approach and some formal rules for solving ordinary partial differential equations, but without justification. Then in the works by Bromwich and some other mathematicians, the methods of Heaviside were justified using the Laplace transform method. And in the works by Jan Kuciniski in the 1930s, he returned to the purely algebraic approach to operational calculus. Dembowski developed his scheme for the hyperbasal differential operators, and then in my PhD I started to work with operational calculus for the fractional differential equations. What is the idea behind any Kuciniski type operational calculus? First we introduce a suitable ring of functions with two operations, and then extend this ring to the field of convolution quotients. And in the field of convolution quotients, the corresponding integral and differential operators can be represented in algebraic form, and that means that we can reduce integral or differential equations to some algebraic equations in this field of convolution quotients, and then solve these algebraic equations and try to represent the obtained solutions that are in general generalized functions as the elements of the initial ring of functions. Let's discuss this program shortly for the general fractional derivative in the Caputo sense based on this recent result presented in this recent paper. So for the details, please see this publication. So the functional spaces are a variant of the space C-1 that we used until now, but we can introduce another parameter, beta, for example, and the element of the space C beta are represented in the form Pavlov function multiplied with continuous function, and the exponent gamma is greater than beta. Normally we will set beta to 1, so then we have just this space of function C beta. But it's a family of spaces, and the general fractional integral has this mapping property, so it works from C beta into C beta. And of course, this operator has convolution representation. Convolution is multiplication in this space of function. And for the convolution by itself, we have also this inclusion. So if we calculate convolution of two functions from C1, then it also two functions from C beta 1 and C beta 2 under this condition, then the convolution belongs to the space C minus 1. So we can work on the space C minus 1 without any complications. And of course, for the derivatives, we need some appropriate spaces. Here we introduce the space C beta m. And this is the space of functions with the property that the fractional derivative of the order with the kernel k in the Caputo sense belongs to the space C minus 1. C minus 1, yeah. Well, the first element of the theory is convolutional ring. As in the case of convolution Kuciniski operational calculus, it's more or less clear and easy to show that this functional space C minus 1 with the operation of addition and convolution is a ring without divisors of 0. It's the content of the famous Titchmarsh theorem. And in this ring of functions, the general fractional integral has just convolutional representation, and convolution is multiplication. It means that in this ring of functions, fractional integral is just multiplication with a certain element. It's clear, but of course this representation is valid for the fractional integral, but fractional derivative is the inverse operator. So we need an element that is inverse to this reciprocal to the element kappa, but the reciprocal element to the element kappa doesn't belong to the ring, and therefore we need an extension of the ring to the field of convolution quotients. And this extension is made by the standard way. So we take a product of two spaces without 0, of course, in the denominator, and we introduce an equivalence relation in a standard way, and then we consider a set of pairs that belong to the space with respect to the equivalence relation. So we consider classes of equivalences on this space C minus 1, 2, and we denote these classes, for example, this like fractions. Of course, it's just a denotation. We could stay by pairs, but it's more convenient to work with fractions. On this field of equivalences, the usual operations of addition and multiplication, just like operation with standard fractions, are introduced, and these operations are correctly defined. They don't depend on the representatives of these equivalence classes, and from the fact that C minus 1 is a commutative ring, we immediately get the result that this triple C minus 1, 2 with respect to the equivalence relation with these two operations is a field that is called the field of convolution quotients. And of course, in a field we can build inverse elements for all elements. The ring of functions is embedded into the field, of course, for example, by using this embedding, and we can define multiplication with a scalar from R or C with this equivalence classes like this, and because C minus 1 is a vector space, then F minus 1 is not just a field, but can be interpreted as a vector space too, with respect to this multiplication with a scalar and with respect to the addition. Just standard procedure. So then we go to construction of so-called algebraic fractional derivative. First of all, it's important to say that most of the elements of this field of convolution quotients are not normal functions. They are generalized functions, so-called hyperfunctions. In particular, the identity element, just equivalence class that contains all pairs with the same element, is evidently a unity element. It doesn't belong to the ring, to the initial ring of functions. It's something. It's a generalized function, and of course, this element plays the role of the Dirac function. In this case. And another important generalized function is the element inverse to the element kappa. Of course, you remember that kappa is associated with the fractional integration, and to express the fractional derivative, we need the reciprocal element to the element kappa, and it can be introduced in this way, for example. And this element is also does not belong to the ring of functions C minus 1, and this element is called algebraic inverse of the general fractional integral. And using this element C kappa, we can introduce the so-called algebraic general fractional derivative of the Caputo type in this form. It's just multiplication of a function f, continuous function f, with this element C S kappa, and here we have additional terms that of course corresponds to the initial conditions. This is a function that is a constant function for all t greater than 1. And this algebraic fractional derivative is a generalized derivative, because you see that we just require that f is a continuous function. We don't require existence of the general fractional derivative of the function f. In this case, the function f should be differentiable, but we don't require this. So this generalized derivative. However, this derivative coincides with the general fractional derivative on the space of function C minus 1, 1. So this is the space where the Caputo derivative exists in the usual sense, and on this space we have this connection. Therefore, I denoted both derivatives with the same symbol, even if in fact these are different objects. This is normal derivative and this is generalized derivative in this sense, but they coincide on this space of functions. And this formula gives us a representation, algebraic representation of the fractional derivative in the field of convolution quotients. So it means that we can, for example, translate fractional differential equations to algebraic equations on the field, and more exactly even to linear equations that can be solved, of course, on the field of convolution quotients. So the same machinery can be done for the n-fold derivative. So in this case, we also introduce this general, this algebraic general fractional derivative of Caputo type in this form. And of course, f should be from Cn minus 1, but it should be not from Cn. For the existence of the normal general fractional derivative of Caputo type, we have to require that the nth derivative of the function f exists. But here we have a weaker condition. And of course, for any function from C minus 1n, where the normal general fractional derivative, sequential general derivative exists, both derivative coincides. and we have this formula. So we have here an algebraic representation of the n-fold general fractional derivative with the kernel k. So we have here just multiplication on the field of convolution quotients. Well, now we speak about so-called operational relations. What does it mean? In particular, we'll translate some differential equations to the algebraic equations in the field of convolution quotients, solve them, but the solution is then a generalized function. The solution is an element from the field. But what we want to get is a solution in the normal form. Solution is an element from the ring. Now, the situation is as follows. The ring is embedded into the field. But when we get an element from the field, the question is if we can represent it somehow as a normal function. This element of the field is a generalized function, and some of them can be represented as normal function. And some of these relations can be deduced in terms of the convolution series that we already have seen. So this convolution series that are generated by the power law series, this are convolution series. They are elements of the ring C-1, and of course this series, they play very important role for this operational relations. In particular, this series, we already have seen this series. So if you start with the geometric series and substitute instead of the function t the j-fold convolutions, then we get this this convolution series is an element from the space C-1, and it's very important element because of this operational relation. It can be shown that the element inverse to the element S kappa minus lambda, where lambda is a real or complex number, can be represented as an usual function in form of this convolution series. And this operational relation is very important. Of course, I put here the equality sign, but of course it's not exactly equality, because here we have an element from the field, but this element can be interpreted as an element from the ring of function C-1. And of course, having this operational relation, we can derive operational relations for more complicated operators, for the operators where we have here reciprocals to the powers of S kappa minus lambda, and then we can use representations as a partial fractions for the rational functions. So this representation is in fact the basic one for many other representations. And in the standard cases, we have the following formulas. In the case of the Kuciniski operational calculus, where the operator kappa is equal to 1, we have here just the exponential function. In the case of the Riemann-Liouville and Caputo fractional derivatives, we have here the Mittag-Leffler function, and this is the kernel of the so-called temperate fractional derivative. You see here that the kernel is a product of a power law function and exponential function, and these kernels, these fractional derivatives, are very important in the theory of stochastical processes. By the way, stochastical processes of non-Gaussian type, so-called Levy flights, are among the most important applications of all this stuff, of these fractional derivatives. So these kernels for the temperate fractional derivatives. And here we have this correspondence. You see, it's a generalization of this formula, and many other important particular cases, of course. Well, as I already said, based on the first operational relation, we can derive more complicated relations just by calculating convolutions of this series. It's not very difficult, but of course the formulas will become complicated. So we can calculate convolutions of the series as some Cauchy products. So finally we get also some different convolution series with special coefficients. Well, now one of the first applications, of course not the only one, is again to the fractional differential equations, and this machinery works like by this simple fractional differential equation. So we have this initial value problem, and first we translate this equation, interpret this equation as an equation in the field of convolution quotient. So we replace this derivative by the algebraic derivative and get this equation. Yeah? So the fractional derivative is reduced to this multiplication, and we have just linear equation. Linear equation in the field of convolution quotients. And this linear equation can be solved, no problem, and then we have this solution in the field of convolution quotients. And then we can come back with the help of operational relations. This reciprocal element is just this convolution series. This is one, and here we have of course convolution in the initial ring instead of multiplication, and this element can be interpreted in this way. So we derive this solution, and of course this machinery can be applied for other equations. Here I mentioned that in a special case the problem we considered here coincides with the problem that was considered by Kochubey in his first work. And if the kernel K satisfies the Kochubey conditions, then it follows from the results by Kochubey that the solution that we derived in explicit form here as a convolution series is a completely monotone function. Because Kochubey showed this, of course, using a completely different technique. He didn't derive this explicit formula, but he proved that the solution is completely monotone. So the same technique can be used for the multi-term equation with these derivatives. Same procedure, and as already said, in the solution we have some rational functions. We can use the representations of the rational functions in terms of some partial fractions, and these partial fractions can be interpreted as some elements of the initial ring of functions, so we get some solutions in the explicit form. Well, we are very good, you see. Just 15 slides are left. We can manage it. And another topic, regarding the operational calculus, of course it's not the end of the story, it's just the beginning of the story. So many things can be done here, like in the case of the Kuciniski operational calculus. We can introduce functions from this element C kappa, different functions. We can introduce calculus of these generalized functions, derivatives of the generalized functions, consider partial differential equations, and all this stuff. Yeah. So, there is another interesting topic here, maybe known for some of you, maybe not. And as we discussed, all the time we spoke about two different derivatives. Yeah? We spoke about Caputo fractional derivative, we spoke about Riemann-Liouville fractional derivative. They are defined by different formulas, and their properties are different. One works on different spaces of functions, one uses different initial conditions, everything is different. And therefore, normally, there are at least two publications devoted to each topic. In one publication, one considers the stuff with the Riemann-Liouville fractional derivative, in another one with the Caputo fractional derivative, and they are somehow different, yeah. But there are many more fractional derivatives. Of course, the story has an advantage because one produces double number of publications. That's also important nowadays. But there is a way to save the work and to introduce some more general objects that combine these both approaches. And this was done, in fact, by Jbashan. Jbashan and Nersesyan many years ago introduced general operators, composition of several integer order derivatives and Riemann-Liouville integrals, but unfortunately their publications were in Russian, yeah, and of course nobody or only few people in the Western countries were aware of these publications. And some of these results were rediscovered, in particular in some works of Rudolf Hilfer. I already mentioned him to somebody in connection with applications, by the way, answering your question. Rudolf Hilfer is director of the Institute of Computational Physics at the University of Stuttgart, and he is a physicist, not mathematician, but he is also very good mathematician, and he published several very interesting and serious works regarding applications of fractional differential equations. So you are welcome to consult. And in particular, he introduced this object. Yeah, you see here a composition of three operators: one Riemann-Liouville fractional integral, first order derivative, another Riemann-Liouville fractional integral. And by particular cases, if alpha is equal to 0, for example, alpha is equal to 0 here. Not alpha but beta. If beta is equal to 0, then the first operator is the operator with order 0, and it's identity operator, and we have here just the Riemann-Liouville fractional derivative. And if beta is equal to 1, then we have here just the Caputo fractional derivative. And of course, for this operator, everything can be done, and was already done. So fundamental theorems, form of the initial conditions, fractional calculus, and so on and so on. So considering equations with this operator saves time and effort, so you cover automatically both kinds of derivatives, and of course many more. And for the general fractional derivatives, we had the same situation. It means we had fractional derivative of the Riemann-Liouville type and of the Caputo type, and we can follow the approach by Hilfer to introduce more general objects that covers both these kinds of derivatives. And to do this, we need a generalization of the Sonin condition. So we introduce here the triples of the kernels, kappa, k1, k2, that satisfy the Sonin condition. For example, these power law functions, these three power law functions, they satisfy this condition if we, under some restrictions on the parameter alpha and gamma, if we use this relation is just nothing else as the connection between beta Euler integral and Euler gamma function. Then it's easy to see that the convolution of these three functions is just the function h1, and h1 is just the constant 1. Yeah? The sum of alpha, gamma, 1 minus alpha minus gamma is equal to 1, and that's why this function satisfies this condition. If we consider these functions, then they are kernels of the Hilfer fractional derivative. So let's introduce a more general operator. It's so-called, I called this operator first level fractional derivative. Why? Because we can introduce second level and nth level derivatives in exactly the same way. It's a composition of two general fractional integrals with the kernels k1, k2, and one fractional derivative. And then for the special cases, k1 is equal to h0, k2 is equal to h0. We recover here the fractional derivatives, general fractional derivative in the Riemann-Liouville type, in the Caputo type, and so we can cover all these things. Yeah? For this power law kernels, under these conditions, we have here the Hilfer derivative, this particular case, but of course we can cover other derivatives. And for this derivative, in the very least, very recent publication published on ArXiv, accepted for publication already, but not yet published, I considered this kind of derivatives, and the first fundamental theorem is also fulfilled, so these derivatives are left inverse to the fractional integrals, and the form of the second fundamental theorem is like this. So you see here that this term becomes complicated, but still it can be derived in the explicit form. And of course, it's also a starting point for further generalizations. So we can generalize the Sonin condition to this condition and introduce this derivative with the arbitrary order. And of course, we can generalize this object to the second level and nth level derivatives. By the way, in the case of the Riemann-Liouville integral, this object was considered by Jbashan already. Jbashan and Nersisyan, yeah, in the early publications. But here we need this condition on the kernels. So all these problems are open. So if somebody has time and maybe fun, please you can proceed with all this stuff. Yeah? Well, regarding references and further results, I already mentioned these papers by Kochubey, for example. With this paper, everything started here, then and this recent survey of the same results by Kochubey, and in the paper written with Yamamoto some years later, 5 years later, we considered some initial boundary value problems for the general time fractional diffusion equations, and showed that the maximum principle is valid under some restrictions on the kernels, and this is also something that goes in the direction of possible applications. So, in this survey paper, by the way, for those who are interested in this topic and would maybe proceed with some results, this survey paper, recent survey paper where theory of this general fractional derivatives on especially fractional differential equations is referred with a lot of references and so on. So then I already mentioned these papers. And finally, I would like to attract your attention to this recent publications by Tarasov. So this is a theoretical paper, but in these papers, he really tried to generalize some standard physical theories, yeah, based on the operators of this type. So here he introduced so-called general fractional dynamics. Here he considered quantum dynamics, non-Markovian. Here he introduced fractional vector calculus, because of course to proceed with physical applications you need the corresponding differential operators. Yeah? You need the fractional vector calculus. Here he introduced this, and recently he published a paper devoted to the general no-local electrodynamics in a very serious journal and also physics already accepted. So you're welcome to look in the case you're interested in applications. So we are ready, yeah? Sorry for the delay, but just 2 minutes. So we are ready, thank you.
But you have more.
Yeah, you have.
Yeah, 10 more minutes.
You were too quick.
Ah, I was too quick.
Yeah.
Sorry. I thought that I should finish at 12 o'clock. Well, nothing to do. We have 15 minutes more for our coffee.
Yeah.
Of course, sometimes I was too fast, but I thought that I should be finished until 12. Yeah, sorry.
Yeah.
Any questions, remarks?
So we have time for discussions probably.
Yep.
I think we should.
So
Yes, please.
you posed then you open problems, yeah?
Oh, no, I would like to ask.
Yeah.
Is it possible?
Please.
So,
Yes,
you gave us a nice presentation of this theory, but I didn't see Laplace transform. Laplace transform transforms all these kinds of calculus, and even Laplace transform is used all the time in the calculation.
Can be used.
Can be
Not
used.
always used, but can be used. Yeah. Sometimes it's
So
used,
then there was a
sometimes
long time, I'm pretty old, and I remember even results of Kuciniski,
Yeah.
but Komatsu already put all these calculus in Sato hyperfunction theory, and he showed that everything can be done also by Laplace transform.
Yeah.
So this approach probably was not considered as pretty complicated because hyperfunctions are very difficult theory with cosmologies and so on. But for me, okay, this is interesting. This only pair which you somehow presented, you and the Terrazzo guy, Terrazzo, and probably other thing, and this is what we use. This only pair because somehow for us it was interesting because there was a big theory what kind of calculi one should use. Not all fractional calculus is good one, and then you actually suggested that Sony pair are good calculus. And this is what we use, but we use this in another way, applying this because my colleague is Atanasio, as you know, and we use this from the mechanical point of view. So always we have some kind of constitutive equation, and then we have fractional for Zener model. Or the Zener model is just extension of Hooke law, which is the oldest one of these laws. And so somehow this part is interesting because then you have some internal conditions which help you to solve equations. We were interested in this dissipative inequality and the use of second law of dynamics. So somehow this part, from my point of view, is also interesting. And then, of course, with Laplace transform, we can do what we, and usually what we get with constitutive equation, starting with wave equation, and then one can get solutions are distributions. And then you can go into classical theory just by applying or assuming that initial conditions are quite good. And then because you have convolution, fundamental solution with that,
exactly.
And then you really can go.
This
is just another point of view of But
thank you for your remark. Of course, you are right, completely right, because what was presented here are the operators of the Laplace convolution type. And of course, it's very natural that one can go to the Laplace domain and work there. Here, for example, in the Laplace domain, I mentioned it yesterday, but you were not there. So in the Laplace domain, we have, of course, very simple relation. So the Laplace transforms, product of the Laplace transforms are equal to 1 divided by p. And of course, in the mechanical papers, mainly this relation is used. These are not quite equivalent relations. Yeah, you know this Kuciniski operational calculus is not quite equivalent to the Dodge calculus that is based on the Laplace transform, because in this case you need some conditions on these kernels to ensure existence of the Laplace transform.
This is
Yeah.
what
Look, if you have a function of this kind, for example, by law, then the Laplace transform doesn't exist. But we can involve this function into the Kuciniski approach.
Take p greater than 1, then you can work with convolution.
Yeah.
You don't have Laplace.
Yeah. I mean, existence of the Laplace transform. Well, in applied papers, you usually suppose that the Laplace transform exists. It's okay. But the Kuciniski approach is a bit more general compared to this approach with the Laplace transform. But in effect, they are more or less equivalent. They are more or less equivalent.
For example, this is something which lives in hyperfunction theory. So you can work with hyperfunctions of subtle and then supported by zero infinity, and then this is all stuff which I also
Yeah. But if you start with the hyperfunction, then in fact you will come in a sense to this field of convolution quotients, more or less. Yeah, these are really equivalent approaches. By the way, are you aware of some recent publications of Polish authors devoted to mechanical models using these general derivatives? Just a moment. Polish mathematicians. It's a pair, yeah. Woman and man. Gorska, yeah. Gorska. Yeah, something like this. They published very recently paper where they consider it really mechanical models in terms of these general operators. Yeah.
Gorska and Korzela.
Gorska. Yeah. Mm-hmm. So there are already things that are similar to your theory, but for these equations, more general equations.
Okay, thank you. Any other questions? Yep.
Professor, to solve a fractional differential equation with variable coefficient, you say like is something similar. But what I see, for instance, in the normal case, you have the integral equation, the differential equation, you put in the integral form, and then you get the solution, but you are losing some things there, like in the classical case.
Yeah.
But as I see here, of course, it's about function spaces, we know now, and maybe it can be improved, those results, like for example, we put integrable, but still you have a better function space, this type of things. Like, but I don't know if it is possible because it's about constant coefficients and everything is working good, but I don't know if you consider or do you think it's possible.
It's standard problem. I mean, even in the field of, in the world of the integer order derivatives and equations, analytical solutions are practically not possible. Yeah? Just for the constant coefficients, for some very special variable coefficients in the form of polynomials, and it's all. Yeah? And then you can study nonlinear equations, but just qualitative properties and numerical methods and all this stuff, even in the world of integer order derivatives, and of course in this case same situation. So with the basic fractional equations, fractional differential equations with the constant coefficients, they built a basis for some other things. For example, if you are interested in studying stability of solutions, then of course the main method is linearization of the nonlinear equations, and then you you have locally equations with the constant coefficients, and that's why this theory with constant coefficients is important. Yeah, but in other cases, of course, you have no chance to get analytical solutions with any method. Yeah, there are no methods. Just in very special cases. Yeah,
Because
here same situation.
Aran, Fernandez is also working with the Kuciniski. He told me like maybe it's possible to do with variable coefficient, but I was like surprised because.
Well, the classical Kuciniski operational calculus was applied also for differential equations with variable coefficients in polynomial form. It's possible here too, but here in this case the polynomial should be not normal polynomial, but this convolution polynomial. In the case you consider coefficients in form of convolution polynomials here, then the same machinery can be used. Yeah. Mm-hmm.
Okay, any other questions? Max?
I have just one final questions. Can these operators contain Adamar operators?
Adamar operator. Adamar operator.
Would
You mean with the
Sonic
logarithmic kernel? Theoretically, yes. There are some publications by Rubin and co-authors, old publications and not very known, where he considered Sonin kernels with also logarithmic factor. Yeah. So Sonin considered just power law asymptotics, and Rubin considered power law asymptotic multiplied with some logarithmic functions. Yeah. So and here another kernel. Yeah. Nice kernel. So and under certain conditions, even as far as I remember, maybe this power sigma, all this, and he derived some classes of kernels in this form. Yeah. So there is a paper written by some co and another co-author from Spain, something like solution of the integral equations of Volterra type with Sonin kernel, something like this. Yeah, you will find citation of this paper in my publications. Yeah, Samco and Cardozo. Yeah. Very good paper devoted to the subject, and then in this paper you will find citations of these papers by Rubin.
Yeah. Thank you. Any other questions? Then let's thank the Professor Luchko. And now we will have almost 2 hours to have a lunch, and we will meet at 2. So, yeah. So today there is no special sandwich, so you